So enthalpy, which is represented by the symbol H, capital H, is used to express or quantify the heat flow into or out of a system. Okay, and we look at enthalpy at constant pressure. Okay, so we know that energy, pressure, and volume are all state functions, and we interrelate enthalpy to being equal to your energy plus the sum of your pressure and volume. So the energy value as well as the pressure and volume changes that occur, okay, are going to give you your overall enthalpic value. So pressure volume work is work that involves the expansion or compression of gases. And we're going to look at this because enthalpy is observed at constant pressure. Okay, so at constant pressure, we know that our work value is going to be equal to negative P times delta V. Okay, so we can interrelate pressure and work by this equation. So let's go ahead and look at delta H at constant pressure and how that interrelates with an equation we looked at in 5.1, which interrelates energy with heat and work values. Okay, so we're going to utilize our enthalpy equation here, and we're going to plug in our delta E value from our equation from 5.1. Okay, so when we plug our delta E value in, which is delta E is equal to Q plus W, we end up with delta H equaling Q plus W plus P times delta V. Okay, we can then use our equation that we utilized or learned about up here. Our W is equal to negative P times delta V, and we can plug our value in for our work value. Okay, and when we do that, we end up with this equation here. Okay, so this equation, you notice that our P times delta V and our negative P times delta V, when we sum them, are going to cancel out. So overall, our delta H is going to be equal to Q. Right? So what that's telling you is that your enthalpy is going to be related to your heat value. We can also represent Q as QP, which represents your heat at constant pressure, which is the specific value that we discussed up here for our enthalpy. The reason why delta H is something that we actually utilize, so this enthalpy value, is because delta H can actually be calculated based on heat exchanges. And that allows us a very easily measurable variable to look at in laboratory settings. So because of this relationship here, this enthalpy being, change in enthalpy being equal to Q, or your heat flow, that's going to allow us to actually perform some useful experiments, as you'll see later on. Now, just like we saw the relationship with energy and exothermic and endothermic reactions, we also see a similar relationship here with enthalpy, right? So it's related to heat flow. So because they're directly proportional, when heat leaves a system, you're going to get a negative delta H in an overall exothermic reaction. When heat is absorbed from the surroundings, you're going to get a positive delta H, and you're going to get an overall endothermic reaction. So we have this very useful variable now, delta H, because it's actually related to heat flow. It's related to Q. And we're going to continue to use this throughout the remainder of the lesson as well as the rest of the semester. So enthalpy, as we just discussed in section 5.3, is something that we use to monitor the heat flow in reactions. Okay, and so delta H, as you can see here, or change in enthalpy, is going to be equal to a final enthalpic value minus an initial enthalpic value. So in chemical reactions, we can look at enthalpic values of reactants and products and use those to calculate our delta H. So in that case, products, which is your final obtained object or resultant, minus your enthalpic value of your reactants. Okay, and this will allow us to actually figure out the heat of a reaction. So the enthalpy change when you go from a specific reactant set to a specific set of products. So that brings us to thermochemical equations. And these are very specific balanced chemical equations that show us a specific enthalpy change for specific molar amounts in a specific reaction. Okay, so in this case, you have an example of the combustion of methane. Okay, so you have oxygen, 1 mole of methane and 2 moles of oxygen, and this gives us 1 mole of CO2 and 2 moles of H2O. This reaction in this specific molar quantity is going to give us negative 890.4 kilojoules of energy. Okay, so in this case, notice we have a negative value for our enthalpy, so this reaction is an exothermic reaction. And what you need to understand is that this enthalpy value is actually determined by the coefficients in the actual reaction above. Okay, so if we were to double or triple the quantity of reactants and products, we would subsequently get a different enthalpy value. Okay, so in this case, 1 mole of CH4, 2 moles of O2, that's going to give us this many kilojoules of enthalpy. There's a few things about the enthalpy of reactions, or that delta H of reaction value that we've discussed, that we need to understand as it relates to thermochemical equations. Okay, so the first thing I want you guys to understand is that the delta heat of reaction is proportional to the amount of reactants present. So the number you see here for this specific thermochemical equation is proportional to the amounts of reactants that you have present. Okay, so if these numbers here, these coefficients were different, the answer, or excuse me, the delta H value that you have right here on the right would be different as well. The second point you guys need to understand is that your delta H of reaction is dependent on the directionality of your reaction. Okay, so if we look at the reaction up here at the top of the slide, notice that I'm taking H2 gas, O2 gas, and I'm producing H2O. Okay, this gives me a negative enthalpic value, right? If I flip this reaction over, as you see down here, okay, and I go from H2O, so basically doing a decomposition reaction instead of a synthesis reaction, I have O2 and H2 as my products. Because I flipped this reaction, the sign has now changed from negative, like we saw up above, to positive, because it's the reverse of the reaction. Something else I want you to notice, though, is that the magnitude of the reaction is still the same. So the amount of enthalpy that is released or absorbed, okay, should be equal regardless of the type of the directionality of the reaction. So whether you're going from products to reactants or the reverse reaction, you'll still have the same overall magnitude or value. It's just that your sign will be different. So the last thing you guys need to understand about these reactions in terms of thermochemical equations is that they depend on the states of the reactants and products. Okay, so I've been telling you that you need to indicate aqueous, solid, liquid, gas, all of those states in your balanced chemical equations. And that's going to be an important feature when we move on to our next section, which is going to have us look at Hess's law and how we can use that to calculate our enthalpies of reactions in a very simple and straightforward way. So let's go ahead and look at a little practice problem here using thermochemical equations. Okay, so the question here asks us how much heat is evolved when 266 grams of white phosphorus burns in air. Okay, so in this case, the first thing we need to do is find our thermochemical equation that interrelates the burning of white phosphorus, okay, to give us our phosphorus oxide product. Okay, so we found that thermochemical equation. We have a very specific enthalpy value that goes along with this reaction. Now, remember, according to rule number 1, or information to know number 1 on the last slide, the enthalpy value is directly proportional to the coefficients or the amounts of phosphorus and oxygen present. Okay, so assuming that oxygen is present in excess because we're burning it in quote-unquote air, so we're assuming we have an excess of oxygen, phosphorus is going to be our limiting reactant. And in this case, we are looking at 1 mole of phosphorus giving us negative 3 3,013 kilojoules of heat energy. Okay, so the mass that they give us for that phosphorus means that I need to go ahead and first calculate how many moles of that reactant I have. Okay, so I'm going to do a basic mass to mole conversion. Okay, this conversion gives me moles of P4. But I also know from the thermochemical equation that my relationship between enthalpy and P4 is negative 3,013 kilojoules for every 1 mole of phosphorus. Okay, so I have that relationship. So if I know my number of moles of P4 and I know my relationship from my thermochemical equation between my enthalpy value and my reactant that I'm looking at, I can go ahead and calculate the amount of heat that's evolved given this molar amount. Now notice also that we probably should have indicated a negative value here on our conversion factor. So our answer should be negative 6,470 kilojoules because it's the amount of energy that's released when we burn that in the air. Knowing that this is an exothermic reaction, that makes sense. So remember that your molar amount, okay, the number of moles is going to dictate how much, the number of moles of your reactant are going to dictate how much energy is released. Okay, but you need to pay attention to how many moles of that specific reaction, relates to your delta H value. So there are more practice problems on page 174 in your book. You can go ahead and work through those. They have some answers there. So this is pretty straightforward calculations. If you have any questions, though, feel free to ask.